and is a professor of immunology, molecular biology, and cell biology. Professor Sinha specializes in molecular oncology and is well renowned for his extensive research on human brain tumors. So, sir, I welcome you to chair this.
Good afternoon, everybody. And first of all, congratulations to the organizers for putting together such a wonderful and comprehensive program. This is a session on the molecular mechanism of pathophysiology in GNE Myopathy. Our first speaker is Dr. Stella Mitrani-Rosenbaum. She is Professor Emeritus of Molecular Biology at Hadassah Hebrew University Medical Center at the Goldstein Savage Institute of Gene Therapy in Jerusalem. She has done a PhD in virology at the Hebrew University of Jerusalem. After a sabbatical at Harvard Medical School in genetics, she switched to human genetics with the HIV project. Since the identification of the GNE gene responsible for the disease, her lab is committed to research on the pathophysiology of the disease and potential treatment of the disease. Dr. Mitrani-Rosenbaum, please.
Thank you very much. Good afternoon to all. I am delighted to be in this amazing country and this city, and I really want to thank Dr. Alok for this invitation. So, what I want to do today is to show you some of the studies that show the other side of GNE, if I can say. So, as we all know now, GNE is the primary cause of GNE myopathy, and we have many mutations worldwide and all along the gene. And we know that this gene is an enzyme that is a key enzyme, in fact, of the synthesis of stearic acid, that its activity is done in the cytosol, goes into the nucleus to be activated, and then the stearic acid is incorporated in the sugar chains in the Golgi apparatus, and these sugar chains go to the membranes and incorporate to the proteins or lipids in there. So here we have the outside molecules of stearic acid. Okay, and we know that stearic acid is an important molecule in all vertebrates and of course also in mammals. They are in all tissues, almost all tissues, and they are very, very important for cell-cell interaction and also in brain development. That's what we know. Okay, so the obvious question or the obvious hypothesis is GNE myopathy acetylation disease, and I know that Dr. Nishino has almost convinced you on that, but I will try to see the other side. Okay, so in fact, what do we know about GNE muscle? GNE in muscle. So what we know is, in fact, the GNE is expressed at the RNA level in almost all tissues, mostly in placenta for development and in liver. We also know that the protein is expressed in most tissues again. Here is an example of neuron tissues. But when we look at GNE myopathy patient muscle, we can see that in fact the GNE protein is exactly expressed at the same level, and there is no decrease in the GNE protein in those patients, okay, compared to normal or to other muscular diseases. In fact, there is no difference in expression and no difference in the localization of the GNE protein in cells in patients. Okay, so what are the GNE protein properties that we know about? First of all, it is a 79 kilodalton protein that is highly conserved in mammalians, and it's allotrophically expressed, as I just said. However, in patients, only skeletal muscle tissue is damaged. And as we have already mentioned that, there is no patients with two GNE null mutations, and we know that GNE knockout mouse is lethal. So again, GNE and probably sialic acid is really important for life. Okay, so in order to determine the role of sialic acid in GNE myopathy, we began by trying to measure first the GNE enzymatic activity in patients, and then the sialic acid molecules in those patients in muscle tissue. Most of the work has been done in muscle cells of one mutation, the Persian-Jewish mutation, N743T, and has been done by Ilan Salama. So first we try to measure the epimerase activity of GNE in muscle cells by radiolabeling chromatography, and what we see in fact is quite a big variation of GNE activity in control healthy people and also in the mutated cells. In fact, the epimerase mutations, we tried two different epimerase mutations, and they seem to be even lower. So we have, as an average, 25% decrease in the activity of the epimerase. We can measure the epimerase activity in the cells only, because the epimerase is the only one that is in the cell, and as you already heard, the kinase is not the unique kinase. There is another kinase in the cell that can use the same substrate, so we cannot do it in vivo in the cells. For that, we express different mutations of the kinase domain in vitro in insect cells, and measure the kinase activity of these different mutations in vitro. Okay? And again, you can see that the different mutations have different levels of activity, and interestingly, the 743 MT mutation has almost no decrease in the kinase activity. Okay, so now that we know that we have mild reduction in the enzymatic activity in the mutations, we want to see if this reduction of activity indeed affects the sialylation level. Again, we are looking at patients with an N743T mutation. Okay, so for that, we quantified total bound sialic acid in the membranes of the cells by oxidation and colorimetric procedure. And what we see, indeed, again, there is a very big variation of sialic acid content in healthy people and also in the affected people. So from these specific studies, we cannot conclude there is any difference in the sialic acid content, total bound sialic acid, not in proteins, and neither nor in glycolipid sialylation. So the total bound sialic acid is not affected. So again, we are talking about the bound sialic acid at this scale. So now what we can ask is whether in fact the mutations in GNE can cause a very subtle difference effect on the sialylation, not at a global level, as we can see in our patients, we cannot see that at all, but maybe at a specific glycoconjugate. Maybe the hyposialylation of a specific glycoconjugate could really affect a certain protein or lipid and then lead to the disease. So for that, what we did is to see if we can have the spectrum of sugar chains in all patients versus controls, and to compare their cyanidation levels. So we did that by many techniques, but I want just to talk about the glycomics technique that we did in collaboration with the laboratory of Andel at the London Medical College. So what we did is protein extraction or lipid extraction of different cells of patients versus controls. So here what we do is, in fact, we match very carefully a patient with a control. That means that we match the age, the gender, and the muscle type of the patients and controls. Okay? So again, we did a protein extraction and a lipid extraction, and then purified those proteins, cleaved the peptids by enzymatic activity, and then what we get is all the sugar chains that are in those cells, and we analyze them by mass spectrometry. So what we get is a profile, for example, like this one, okay, of all the different sugar chains that are in this sample. Okay. Each symbol here is a symbol of one sugar. So these are the different compositions of the different sugar chains, and at the end of the sugar chains, of some of them at least, you can see the sialic acids. Okay? So we did that for controls, and we compare them to the patients, and in terms of the spectrum of sugar chains, we cannot see any difference. The same sugar chains are present in both control and patients, okay, in the different patients. We did the same for the lipids, so we isolated the sugar chains that are bound to the lipids, and again, we couldn't see any difference in the spectrum of the chains. So the same sugar chains are present in both patients and controls. Okay, so now what we wanted to do is, in fact, to look at the cyanidation of those sugar chains. For example, here you can see a sugar chain, okay, with no sialic acid, then the same chain with one sialic acid, one cycle later, and the same sugar with two sialic acids. Okay, so we have one molecule, no sialic acid, monosialilator, disialilator. Okay, and we try to calculate